Hi students, this is Professor Golestane. I am supplementing the previous lecture with this video lecture, so perhaps certain things I could make more clear for you. We talked about the crystal field theory last time, and I want to emphasize certain things about it. And the whole theory is based on ligands experiencing repulsion from the d orbitals. So the electrons in the ligands, I'm going to highlight certain things for you. The electrons in the ligand, and you know that ligands have lone pairs of the electrons on them, and that's how they bond and they form a covalent bond with the metal ion. These ligand electrons, they repel the electrons in the unhybridized d orbitals of the metal ion. And remember, we talked about the d level electrons, that they had certain amount of electrons in them depending on the metal ion. And so this is not the next level d that's hybridized with the s and p, which creates the bonding, but these are called unhybridized d orbitals of the metal ion, and they have a certain number of electrons in them. So what happens as a result of this repulsion? The energies of the d orbitals are split. So this is what's important that I mentioned to you last time. And this splitting of the energy is called crystal field splitting energy, and I showed it to you with the symbol delta. And there are ligands that really create a lot of splitting. We call them strong field ligands and weak field ligands. Strong field ligands create strong field splitting, and weak field ligands create less splitting or weak field splitting. So let's move on. So we talked about this particular splitting pattern that happens to octahedral complexes. And octahedral complexes, I told you last time that you should know your d orbitals. So there are d orbitals along the xyz axis, and there are d orbitals that are off axis. So I mentioned that the off axis orbitals, they experience less repulsion, and the on axis orbitals, they create a greater repulsion. So that's how that splitting takes place, because of the amount of repulsion. Okay, so let's move on. We've talked about some of those, and I've shown you some of these diagrams. I'm just sort of moving toward the end of the chapter so we can complete the lecture using these PowerPoint slides. So this is what happens, is that when you have these are the unhybridized d orbitals here, that you have certain number of electrons in them. And for example, the first row of the d are the 3d levels, and there are so many electrons in here. And these electrons, together with the lone pair of the ligand, cause the splitting. So this is called the octahedral complex splitting pattern. And you can see that the on-axis orbitals are sitting at a higher energy level. Something that we will talk about is the color. I think I talked about it last time, but I'm going to review it for you again. So the color of the complex ion is due to electronic transition between the split d sublevels. For example, if you have your lower level and the higher level, and this is your delta, the splitting energy delta, if you have an electron here, and if there is space for the electron to go to the higher level, the difference in this energy, this is really energy difference, the difference in energy is the portion of the wavelength of light that's being absorbed. So if you shine some sort of light or energize these electrons, The electron, if it gets the right amount of energy, it will excite itself to a higher level, and it absorbs a certain energy from the electromagnetic spectrum. And if a portion of energy of visible light is removed, therefore the leftover that your eyes see is the perceived color. So typically we say the complementary color is what you see. There's an absorbed color and there's a complementary color. So I'll show you that slide again. So we talked about this size of that energy gap delta that I mentioned. So I'm going to, oops, sorry. Oops, okay, I have to go back to my slide here. So the size of the energy gap depends on the type of ligands. Strong field ligands are cyanide, nitrite, ethylene, diamine, and ammonia. And the weak field ligands are starting with water, hydroxide, fluoride, chloride, bromide, iodide. I think last time I mentioned to you that fluoride is among the strong field, but it's not. So typically the strong fields, they contain nitrogen as the atom that donates electrons to the metal ion, and the weak field typically have the oxygen and the halogens as the ligand, and where the lone pair is on the ligand. And also, I also mentioned that the size of the energy gap delta depends on the particular metal ion. Typically, higher charged metal ions, they tend to attract the ligand electrons more strongly, creating a greater level of repulsion. And so that you don't have to really know why so much. All you have to know is this series of what's weak field and what's strong field, and I typically provide that to you. You don't have to memorize what's weak field and what's strong field. So let's move on. And this splitting also determines the magnetic property, because electrons of the d orbitals feel differently depending on the splitting. So they can cause unpaired electrons, and the unpaired electrons create magnetic property as well. So I've adjusted this diagram because the PowerPoint that I have on the one that I referred to when I lectured in class had some mistakes in it, and I corrected that. So please make a note of this. For example, if you have a cyanide ligand which creates large splitting, therefore when you put 6 electrons, and this is an F or iron in the state of Fe, I'm sorry, not F, Fe iron, and we need to determine the oxidation state. The overall charge is 4 minus. Cyanide is 1 minus. There's 6 cyanides, so this creates a 2 plus. 2 plus minus 6 gives you a 4 minus. So we are dealing with Fe2 plus in both cases. Fe2 plus has a total of 6 d electrons. So we call it a d6 ion. So for a d6 ion, if you have a large splitting, you're supposed to fill the lower level d's first and then go to higher level, because the energy is large, and so the electrons, the pairing energy is the energy when the electrons pair into the same orbital, is less than the energy or the splitting energy. So electrons just prefer to fill the lower level. And when you have a small splitting in the right side with water, Fe2 plus with water is a weak field ligand. It creates a small splitting, and so your 6 electrons should be filled as lower level first, then go to the higher level, and then you simply come back to the lower level and put. This is sort of like filling all the d orbitals in the same way that you fill if all of the orbitals were at the same energy, because in this case the splitting is small and the pairing energy is higher than the splitting energy. So the orbitals don't pair unless they have filled completely, all of them, and then you come back and you start pairing. So now look, on the left side, all of your electrons are paired. So this is a case of what we call diamagnetic, and also we call it a low spin complex. So when there is a low count of orbitals with single spin, remember single spin is spin up direction that we typically put as the first electron going in. When you have low spin, you don't have too many of this. In this case, you have no orbitals of low spin. On the other hand, for a paramagnetic situation of the aqua complex, you have more, like 4 single spin orbitals. This is called a high spin complex. So this can the complex to the right can be magnetized, whereas the complex to the left cannot, because all the electrons are paired up. And we talked about magnetic property last time. So I mentioned about the color. So you perceive different colors of these different metal ions because of the ligand field, the repulsion field of the ligand. So I showed you this last time, but I'm going to show this one more time. So this particular ligand complex that's placed in here, it has a reddish violet color mixed in it. So if you are looking at this and light, visible light is going through the solution, on the other side you see it as a reddish violet color because the yellow and the green is being absorbed. So notice that the yellow and the green is the complementary color to red and violet. So the yellow green is absorbed by the complex ion, and then the color that you see, the complementary color, is what you see. And you can see at the absorption spectrum, we have a lot of absorption in the yellow-green zone. It's a broad spectrum, but majority happens to be in the yellow-green zone. So the complex color is reddish violet, which gives you this sort of like a darker violet color. So please know this complementary color circle that I showed you last time is called color wheel. You should be able to draw the color wheel and determine the color that you see based on the color that's absorbed. If you only absorb a green color, you see a red. If you only absorb a yellow color, you see violet. Okay. And if you absorb, say, green, yellow, and orange, you're going to see a mix of blue, violet, and red. And essentially, it turns out to be the violet. The middle color is the mixed color that we see here. Okay. All right, let's move on. So here is a diagram. This is a good diagram that it comes from another textbook, from your textbook particularly. And this diagram shows that if you have different complexes of chromium, these are all chromium in a +3 state, but now you have a different ligand in each case, which creates different splitting energy or different ligand field strength. And the splitting pattern is going to be different. The highest splitting happens with cyanide. So this is the splitting energy right here, delta. And it changes actually. So this is the delta, and it keeps increasing because you keep changing the ligand. So you have the greatest splitting with the cyanide. The least splitting is with the fluoride. So you can see that the color changes. You go from green to violet to yellow, and both of these are pretty much high splitting energy, and the color is yellow. So you can see that, for example, we mentioned that the electrons, they actually excite when light is hit upon them. They get excited to the higher energy level. So this is the amount of energy that's absorbed. Let's just forget about it. So that's what's being absorbed. So you have situations where there is low energy that's absorbed for the green complex, and for the yellow complex we have higher amount of energy. So going back to this, you can see where when you're absorbing a higher amount of energy, you are seeing a lower energy color. For example, if you absorb this color violet, which is higher energy color, then you're going to see yellow, which is lower energy. If you looking at this is the one that I was showing you, the yellow one. If you go to the green one with the fluoride ligand, so the green one is low energy of absorption, so it's relatively on the red side. So you're going to absorb this color, which is red, and you're going to see the complementary color, which is green. Okay, so please make a note of this. This is a good diagram to show you the color that's absorbed and the color that's seen. From the color that I see, I can determine what color that's being absorbed. Remember the complementary relationship. Now we're going to the tetrahedral geometry and crystal field splitting. So I'm going to pause the video. Actually, I'm going to stop the video and actually make another video for that, because I think from now till the end, maybe there'll just be one more video. Okay.